All right, thank you. Right, so it used to be that in this course we would spend 2 full lectures on a fast Fourier transform. And at some point we realized that we were confusing people more than we were teaching. So somehow cutting it down to 1 lecture ended up being more effective. So we will not be talking about fast Fourier transform. I'll just encourage you to look over the materials in the book, right? So we covered 1 view of the fast Fourier transform last time. That is the sort of direct recursive view. There is also a matrix version way of thinking about it as a linear transformation. And also we didn't cover the inverse of the fast Fourier transform, but I understand it will be covered either in section or in homework. So make sure you understand that as well, okay? So we will leave multiplication algorithms behind, which actually have dominated the first few lectures. And now we'll talk about something a bit more combinatorial rather than algebraic. And we'll start a sequence of lectures on graphs, okay? So next few lectures, we'll want to understand combinatorial object of graphs, okay? And ask a number of computational questions about graphs. Now again, graphs are fairly sort of foundational modeling tools. Like they show up all over the place. You can think about, I don't know, finding directions on a roadmap. That is a graph problem, right? You want to find the shortest path from one point to another according to some notion of sort of cost, right? You can also think about analyzing communities, like for example in friendship graphs, like on Facebook, right? So you have sort of connections to your peers, either through friendship or relationships or acquaintances, right? And you can try to study these communities by sort of looking at different types of edges and asking various questions about how the graph looks like. The internet itself is actually not a central architecture. It's a federated architecture, and it's made up of a bunch of links that together forms the internet. So you can try to study the internet graph. Your brain is also a graph, right? So there are people that will actually go ahead and take sort of brains and try to sort of tease out what is all the connections in the brain. Is actually something called the Human Brain Project, okay? That is ongoing right now. It's funded, it's an international project whose goal is to get to the point where you can have, say, a human brain basically mapped out every single connection inside it, kind of analogous to the Human Genome Project, where you wanted to sort of have the list of all base pairs in a human DNA, right? These days you can also talk about like a Bitcoin graph, right? So these are transactions that happen over time, and sort of the edges denote movements of money from one account to another. So, okay, and you can go on and on and on. So the graphs happen all over the place. So from a computational perspective, we want to be able to solve questions about them. Okay, so that should be clear. Okay, so the first question, so today will be, I think, so partially a review for some topics you probably have seen in some other lectures. Maybe some of the topics will be new. And so the first thing we should clarify to ourselves when we talk about a graph is how we represent it, right? So a graph is a pair, okay, that is given by the vertex set, V, and the edge set. Okay, so V are the vertices, just a set. And E are edges, and it's just a subset of the Cartesian product of V cross V, right? So it's pairs of vertices. Okay, and typically in this class we'll distinguish between undirected graphs, where the edge relation is symmetric in the sense that if you have some edge, say U and V, and it's an edge, then it is also the case that the edge VU is an E. Okay? So here maybe the analogy would be that maybe roads for the most part are undirected because kind of the distance you cover going one way or the other kind of looks the same. So maybe you're going to call that an undirected edge. It's not always true, right? So for example, in the Bay Bridge, you have a toll plaza on one direction and not on the other, whatever, right? So But maybe it's not always like that. Sometimes it's explicitly not like that. For example, in a brain, you have sort of connections going in specific directions. Like synapses work usually in one direction. Okay? So we also talk about directed graphs where sort of we don't explicitly require that the edge relation is symmetric. Okay? So that's the object we want to study. And the questions about directed and undirected, I think you should have seen these notions before. Okay? And you could represent graphs in many ways. There are two sort of, at least sort of two basic ways to represent it. Graph. So again, you probably have seen this already. So what's one way? Let's start with the matrix, it's the easier one. So it's called the adjacency matrix. So basically, you allocate an sort of n by n matrix. By the way, usually I should also add up there. It is typical convention that we denote by n the size of the vertex set, so the number of vertices, and m the number of edges, right? So, and the number of edges could range from anywhere from 0, maybe there are no edges, right? It's a very uninteresting graph, to maybe order of n, to as much as how much? N squared, right? So there's all the possible possibilities, right? So E will never be more than n squared simply because, those are all the edges you could have talked about. So in the adjacency matrix representation, you allocate sort of an n by n matrix. So it's n by n. And in the ijth entry, mij, Jesus, this thing really writes terribly. Let's see if we can find a better one. We're going to put in the ijth entry, we're going to put a bit, okay, which denotes if ij is in the edge set. Okay, so very simple. We just put down all the n squared possibility of edges, and we put a 0 if the edge is not there, and we put a 1 if it is there. Okay? So this is so a very explicit way to talk about representing a graph. The other way of representing a graph is through a list, right? So we can call it also the adjacency list. By the way, why are we talking about adjacency? Because we're talking about which vertices are adjacent to which other vertices by virtue of having connections to them through edges, okay? In the adjacency list, basically, we are going to take an approach where we put down the list of all vertices, so v1, v2, up to vn. Okay, these are all the vertices. And for each vertex, we're simply going to associate the list of its so-called neighbors. So those are the vertices with which they share an edge. Okay, so maybe v1 will share an edge with, I don't know, v3 and v4. But maybe it doesn't share an edge with, say, v2, so we don't put it there. Okay? Maybe v2 is very popular, maybe, and so it shares an edge with v1, v3, v4, v5, and potentially many other people. Okay? And so if v2 shares an edge with many other vertices, then the list will grow, right? And so on and so forth. And of course, when you write down either of these two things, you need to kind of decide what kind of data structure you're going to allocate. We're not going to be spending too much time thinking about data structures in this course. It's not a data structure course. But obviously, when you kind of put this down, so in a real implementation, you should worry about these things. That said, at a very high level, I wanted to at least comment on the sort of the key differences between these two representations, because they have some sort of sharp trade-offs between the two. And without getting into details of data structure, let's just try to reason about them at high level. Just move this one. So let's just do a quick comparison between the two representations. So we can talk about the list, or we can talk about the matrix. And when we sort of work with graphs, and so we have some algorithm running, we may be interested to kind of ask various questions to the representation of the graph so that we can continue with the algorithm. So one question would be, oh, I have some particular edge in mind, UV. Is it in the edge set? OK, so I'm running the algorithm. At some point, I have across some particular edge, UV, and I'm wondering, is it in the edge set or not, right? So if I have the list representation or the matrix representation, what do you expect this kind of query to cost us? So let's maybe talk about the matrix first. Huh? Constant, right? Order of 1. Because I have the index U and index V. I just go directly into the entry. I see whether there is a 0 or 1, and I answer according to that. In the list, it's not quite constant, right? Because I would need to pick either U or V, or let's say U. In a directed graph, you should really have to pick U. I go down here. And then I have to look whether I will find V somewhere in the list. Right? But a priori, I don't know whether I will find a short list or a long list. Right? So I may have to travel a while until I finish the list. And maybe I find V before the end of the list, or maybe I never find it, in which case the answer is no. Right? So at least without doing any sort of very clever tricks, this is going to cost me order of V. Right? So it's a very different type of cost. This is in the worst case. Right? For graphs where maybe all vertices have a small number of neighbors, then it certainly won't cost me this much. But for general graphs, it could cost me as much as that. OK? So OK, that's one type of query. What if I want to find the neighbors of a particular vertex U? OK, so I don't have an edge in mind now. I have a vertex in mind. OK? And I want to retrieve all the neighbors of this A vertex. In the matrix representation, how much will it cost me? N, right? Order of V. Why? Because if I'm interested in a particular vertex, I just say, look at this row, OK? And the row corresponding to U. And I start traveling in the row. And I figure out all the places where I find a 1. I don't know if and when I will find the 1. So I really have to travel the entire row. Also because after I find 1, it's not enough to just return that. I have to continue because I'll find all the neighbors, OK, of that vertex. So I really have to travel the entire row. In the case of the adjacency list, how much will it cost me? Yeah, so again, this goes into implementation issues. Do I return a pointer to the list, or do I just actually literally return the list? So let's be pessimistic and say that this will cost me order the degree of U. What is the degree of U? Well, that's the size of neighborhood of U. OK? So in the worst case, you may have to literally physically take the list that's sitting there, and you have to return it. Again, you may not necessarily have to do that. Maybe you just return a pointer to it, and some other routine uses that. And for now, it's just a constant time operation. But so morally, sort of, there is an object of size degree of U sitting there. OK? And maybe another thing that may be worth to discuss is the space requirements. OK? So just in memory, how expensive is it to allocate the again, I'm not being precise, data structure that represents each of these? In the case of a matrix, how much will it cost me? N squared, right? And in the case of the list, order of N, right? Because every vertex appears order of V. Because look, I don't have to, E. Because notice that each of these pairs is precisely a vertex, right? And I'm writing down basically all the vertices one after the other, OK? In particular, if there are vertices that maybe have no edges, OK, let me put it differently. You might wonder, what happens with n? What if there's many, many vertices that don't have any edges? Well, call them all together. Bucket them all together and say that all of them have no edges, right? But typically, we always take graphs where every vertex kind of participates in the graph in some way. If there are some isolated vertices, then just forget about them. Why are they even there? Okay. So maybe you would want to say here order of E, assuming that that E is at least V. Okay. So if it's not, then you may have to do some more data structure tricks to actually paste something closer to order of E. But the point is that I wanted to highlight here that there are trade-offs between these two, and in some cases you might want to use one or the other. So for example, if you have a graph that has very few edges, you may want to consider an adjacency list representation, provided that sort of you're willing to put up with the other costs here. Or maybe you'll pick some other trade-off. For many of the algorithms we'll talk about, since we will be discussing arbitrary graphs, which could be as much as v squared, we won't really pay attention to the difference between the two. Sometimes we will. Okay, and I'll bring it up whenever there's a difference between the two. Okay? Okay, so we haven't talked about anything about algorithms yet. This was just, here's a graph, the definition of a graph, here's how we could represent it, and here are some trade-offs between them. Any questions? Or any mistakes on the board? Okay, so let's do some algorithms. And first, let's start with simple algorithms. We're going to ask a very simple question about the graph. We want to understand connectivity of the graph. Namely, we want to understand what are the connected components of the graph. It's a very simple and fundamental structural property. We could ask about it, right? It's not quite the same as clustering, right? Because maybe when you study communities on a graph, you want to understand clusters. These clusters maybe are still connected. So, but you can think about it as kind of like that, right? We're just trying to understand which vertices are related together and which vertices are sort of not related to them, right? That's about connectivity. So when we study connectivity, there is a fundamental algorithm that so we'll talk a lot about today. And the algorithm is called depth-first search, okay, which you probably have seen already. But today, I think, hopefully, we'll say some things that maybe you haven't seen already. Depth-first search. Okay, and the goal of this algorithm, we'll see very soon, it tells us a lot about the connectivity structure of a graph. So before talking about depth-first search, I want to introduce a very useful and highly recurring sort of a recursive subroutine. Okay, this subroutine will appear in many other algorithms we'll see, so it's important to understand it well. Okay, so I'm going to put it here. It's going to be the explore subroutine. Okay, so it takes two inputs, the graph. Okay, and it also takes as input a vertex in the graph. And the goal of explore is basically to start at the vertex v and find out all vertices that are reachable from v. Okay, it's a very simple goal. You might wonder, well, why is it not the same as depth-first search? Can anybody answer that? So I said, I want to understand the connected components of the graph, right? And I said, we're going to talk about depth-first search. I say, well, hold on a second. We'll talk about it in a moment. I want to first tell you a subroutine, explore. The goal of explore will be that it will start at v and look for all vertices reachable from v. Okay? So how is this distinct from depth-first search? Yes, question. Yeah? It terminates upon finding what? The what, sorry? And I'm not do we have a goal node here? So we have a start node, right? So maybe what I was trying to get at is that maybe the graph has two components, right? And so if I start in one place, I'll definitely never reach the other one because Explorer doesn't understand those things, okay? So Explorer has a very specific task. It says, here's a starting point. Please figure out everything is attached to it, the end, right? So it may not know anything else about the graph. I mean, it knows the rest of the graph. It's given to it as input, right? But it doesn't have a responsibility to travel anywhere else, okay? Yes?
Is Explorer only looking at the neighbors?
Well, now I'll define Explorer so that we can talk about it. So the first thing it's going to do, it's going to say, it will set a flag on the vertex v that says visited, and we'll set it to true. Why? Because we invoked explore on v, so we've clearly visited it. After that, it will consider all the neighbors of v. Okay, so for every vw in E, okay, notice that the w here ranges over all the neighbors of v. What it's going to do, it is going to say that if we have not visited w already, we're going to explore it. Okay? So this is the entire definition of explore. All right? So it considers every edge coming out of V, and it considers all of the neighbors one by one. If they have not been visited already, then it will explore them. If they have been visited already, it means that somewhere else, for whatever other reasons, Explorer has already been run on them, so we're not going to run it again. Okay? All right, now we're going to prove a very simple claim. And the claim is that Explore really does explore everything reachable from V. Okay? So, claim. I have this weird chalk. The claim is that we visit this thing. I just want a nice chalk. So much to ask. All right, let's try again. So it visits every vertex reachable from V. Okay, that seems like a simple claim, and it is a simple claim. I just want to take the time to briefly prove it, okay? Because it feels intuitively clear, right? I mean, just look at how Explorer is working. I really ought to find every vertex reachable from V, right? But when you work with graphs and you want to sort of convince yourself that an algorithm is working well, there are certain proof techniques that end up being useful when you look at more complicated algorithms where maybe intuition is not as strong, okay? So here's a way to prove this claim. We're going to do it by contradiction, okay? Suppose, by way of contradiction, that there is some vertex reachable from V. Let's call that vertex A, that is not visited when you run explore on V. Okay? So here's V. And because A is reachable from V, there is a path. Notice this path may have nothing to do with what the Explorer was doing. I'm just saying A is reachable from V, so there is a path. And we're assuming, by way of contradiction, that A is not visited. Okay? So let's look at this path. And let's look at somewhere along this, for every vertex here, we can ask, has that vertex been visited? We know certainly V has been visited. We know A has not been visited. Somewhere along this path, there will be a first vertex that has not been visited. Maybe it's A, or maybe it happens before. OK? You agree that such a vertex must exist. So let's take that vertex and call it, I don't know, B. B. So this is the first not visited. OK, so it's the first not visited. So it means that this has been visited, this has been visited, this hasn't been visited. In particular, there is a vertex immediately before B. Let's call it W. That has been visited, right? Because B was the first that is not been visited. OK? So this one is visited. OK? Are we together? I mean, we're together in the same room. Are we together for the with the proof? OK. All right. Now, because it is visited, it means that we ran explore at some point on W. Right? Now, let's look at what explore did at that moment. It considered every edge coming out of W. But look, here's an edge coming out of W. It must be one of those that are considered here. And because we said that B was not visited, then this condition actually holds. It is not visited. But then the algorithm says we should explore that B, and then we should have visited it. OK? So that's a contradiction. Does it make sense? Well, it's like so elementary here, OK? But kind of clarifying to yourself, linearizing the logic, and making sure that you understand this proof will help you a lot for more complex algorithms later. There's a question. Yeah. So here I'm taking, because B is the first not visited vertex, the one immediately before it must be visited. And so I'm focusing my attention on what happened the moment that explore was run on it. It must have been run on it because it's visited. OK? All right. It's a simple proof, and it shows that, indeed, the explore procedure visits every vertex reachable from V. OK? But contradiction proofs are your friend when you study graphs. OK? Anyway, more questions about it? Yes?
Is this algorithm for directed graphs, undirected graphs, both?
So far, it's for both. Whatever I said doesn't rely on directedness or undirectedness. OK, so now that we have Explore, how do we assemble the depth-first search procedure? And actually, we will be modifying it a few times. But yeah, nonetheless, let me put it here. So now I have a procedure that says, start off somewhere. It will, boom, explore everything that is reachable from a V. OK? So if I want to, say, explore the entire graph, certainly I should sort of initialize all the vertices at the very beginning with visited being false. OK, so that's the first thing I'm going to do. I'm going to say, for every V in V, we're going to set visited, the flag, visited, V to be false, right? Because we haven't done anything so far. And then, for every vertex in V, we're going to say if the vertex I'm currently considering is not visited, then I'm going to run explore on it. So let's kind of imagine in our head what's happening here. When I start this algorithm, I set all the flags to be false because I haven't done anything. I consider all the vertices in any order. It doesn't really matter which order. Say I pick the first one. Clearly, it's the first one, so I'm running it because the flag is false, so this condition kicks in. So I'm going to run explore from V. Because of this condition, I'm going to be visiting everything that is reachable from V. OK, so in particular, we'll mark the flag to be true on everything that's reachable from it. So the next time around, when I come back here, maybe the next vertex has already been visited, so I'll skip it. skip, skip, skip. In particular, I will skip every vertex that is reachable from V. The next time around, maybe I'll reach to something, a V, or V prime, that is not reachable from V. That guy must be have the flag equal false, and I'll explore that, and I'll reach everything there. Okay? Now, as is, this algorithm is not very interesting, because at the end, when you're running it, what do you see? You started out with a graph. You set all the flags to be false. You finish running the algorithm, and all the flags are true. Good job. Right? So it didn't do really anything useful. Okay? So now, what we want to do is to build on this kind of skeleton of an algorithm to start doing something useful. And we'll start doing that first for undirected graphs, okay, which are kind of the easier ones. Because undirected graphs have a lot of structure. They have the structure that whenever you go from U to V, you're guaranteed you can go back from V to U using the same edge. Okay? Before we do that, though, I want to just close the discussion of depth first search by talking about, before it gets more complicated, its running time. Okay? You say, why are we analyzing the running time of a useless algorithm? Well, because all the other algorithms we'll do that are useful are small variations of these, and so might as well understand the running time of an algorithm while it's simple. Okay? How should I analyze the running time of this algorithm? Yeah? Excuse me? The amount of time. So I think sort of so this part is clear, right? So we're paying a order of V. Okay, what's less clear is this part, right? Because we have this recursive procedure explore that does some work that depends on vertices and work depends on edges, right? Notice that there are some explore calls that could be very expensive right away. Imagine that there is some vertex that has a lot of neighbors, right? And so the cycle here, the loop, will have to consider every edge. Okay, and maybe there are other calls where the vertex has one neighbor, right? And then this loop will happen only once, right? So I just want, this is not a very difficult thing to analyze, but I just wanted to highlight that it has a recursive structure, and because of its recursive structure, you may be tempted to go down and write a recursion for it, which is what we've done for the past few lectures. And this is precisely what you should not do for this algorithm, because if you write down a recursion, you will derive an upper bound. It will be a terrible upper bound. Okay? So what we want to do is do some sort of more global accounting, some sort of higher level observation about what is the total cost across all the graph, right? Because for some vertices, there might be many edges. For other vertices, there will be fewer edges. So what is the point? What is the observation to try to get a handle on the running time with this algorithm? Yes? Are you sure number of, yeah, another way to put it is maybe we should focus on the edges, right? Sort of, how many times do we touch every edge, for example? Yeah. Yeah, at least once, but we need to put an upper bound. Suppose if we visit it n times, that would be a bad thing, right? Because we'll get n times m, right? How many times do we visit each edge? Twice, right? Also, visit is overloaded, sorry. Like we consider, right? So we consider each edge twice, okay? Once, whenever we're exploring one endpoint, and the other time when we're exploring the other endpoint. The end, we are not exploring either endpoints any further, because when we are exploring an endpoint, we set it to be visited. We'll never touch it again, right? Again, think about it. When are we considering an edge? Only whenever we are at either endpoint. Why are we at an endpoint and considering an edge? Because we're exploring that endpoint. How many times can we be exploring an endpoint? Well, at most once and exactly once, because we are exploring whenever it has not been visited. If it has been visited, we are not exploring it again. OK? Yes? Excuse me? No, this accounting will actually work also for directed graphs. And then the way you modify this accounting is that we're only considering each directed edge once. OK? So because you can view an undirected edge as two directed edges going either direction. So my argument would work also if you just say I consider every directed edge exactly once, whenever I am exploring each source vertex. Yes? I am marking the other endpoint when I explore it. If it could be that I'm considering an edge and it has already been explored, the other endpoint, so I don't explore it. Right? But I still paid for the edge, right? I still had to pay for the edge to get there, right? So the running time, basically in the end, is order of V plus order of E. And the point here is that we're exploring each vertex once. And we consider each edge twice. Or alternatively, each directed edge once. OK? So it's actually a very cheap algorithm. Again, does nothing, so might as well just stay at home. Would have been cheaper even still. But it's linear time, right? So it's basically the time. It's a constant of the time to read the input. OK? And if you sort of paint this algorithm in your head, that's basically what it's doing. It's just reading the input in a sort of in a certain deliberate and order. The recursion here, by the way, it's it's implicitly implementing a data structure, the recursion. What is the call stack of this recursion doing? Well, we'll make this explicit now. All right, so let's talk about, so much for the running time. So that was the skeleton of the algorithm. Now let's really talk about connectivity for undirected graphs. Undirected graphs. So we're going to say that U and V are connected if there is a path that goes from U to V. And in fact, so maybe let me make the path a bit wiggly, meaning that it's not a single edge, it's a path. Okay? Obviously, if you can go from U to V, because it's undirected, you can also go from V to U. Okay? So that's the definition. So say that U and V are connected if you can sort of, there's a path between them. And then we're going to define a connected component to be a subgraph, or rather, the connected components to be the subgraphs in which every vertex is connected to every other. Wait, this is a sort of, putting in English these things is just messy. Essentially what I'm saying is connectedness is a so-called equivalence relation, right? It is it is, I guess, reflexive because you're connected to yourself. It is symmetric because if you're connected to U, if you're connected to V, V is connected to U. It is also transitive in the sense that if U is connected to V and V is connected to W, then U is connected to W. And as you know, equivalence relations partition a set into equivalence classes. So this means that you can view a directed graph as a set of subgraphs, each of which is made up of things that are all connected. Okay? These are the equivalence relations, the equivalence classes. So these are connected components. And what we want to do now is actually do something useful, which is we're going to take a graph, undirected graph as input, and we want to spit out the connected components. Okay, so we've computed some structural information about the graph. So that's what we want to do, and we're going to do it by sort of do some simple modifications to this explore and depth first search. Let's do them here. Let's call it connected components of G. Okay, so what we're going to do is we want to find the connected components of G. And so we're going to start out like before by just setting this visited flag to be false for all of them. So for every v in v, we're going to set visited flag is false. We haven't done anything yet. We're also going to maintain another piece of information about every vertex, which is the connected component they belong to. So we're going to call it CC num for connected component number. Okay? And at the very beginning, we don't know anything, so we're just going to set it to bottom. Okay? Just some uninitialized or null or whatever. Okay? So at the end, what we want to do is want to assign numbers so that they define the partition of the graph into connected components. Okay? So we're going to start out by saying, OK, let's have we haven't discovered any connecting components so far. And now we're going to say for every vertex in V, if it is not the case that we have visited it before, then what are we going to do? We're going to say, OK, if I haven't visited this vertex, it means that I am about to meet a new connected component, right? So let's increase the counter of which connected component we are at, OK? And we're going to explore from here onward. And of course, I need to modify explore so that whenever I'm in the exploration, I assign to every vertex that I encounter the counter CC num. Okay? So I'm going to modify explore. So let's call it this is the modified explore GV. This is going to be a modification to do the bidding of this algorithm here. I'm going to say, OK, we're going to say, like before, visited of V is true, right? We have to set the flag. And then, crucially, we have to set, OK, now I'm visiting this vertex. Let's assign to it the current counter. OK? So in here, maybe, maybe. So no, so this is an array, right? So, and this is a counter, OK? So maybe a CC, maybe let me call it CC CTR for counter, OK? CC CTR. And here, I'm going to set the connected component of this one to be the current counter. And then I continue like before, right? So I need to consider every vertex, so every outgoing edge for VW in E. If the neighbor is not visited, then I explore it. OK? So again, the only differences from before was that we started out by just setting all of the sort of assignments to the partitions to be sort of uninitialized. We have this counter here. We increase the counter every time we encounter a new connected component. And within explore, we assign whatever the current counter is. Right? And so because Explorer will explore everything that is reachable from V, by definition, that is the connected component of V. Okay? It will assign the same counter to everything there. And when it's done, we'll come back here, right? And the next vertex that we'll encounter will be something that necessarily is outside of the connected component of V. So we're increasing the counter, and we're exploring from there. Notice that it doesn't matter from which vertex I explore a connected component, OK? Yes?
Yeah, so part we're going to first part we're going to see
Yeah, I'm just saying null, OK? Just uninitialized. OK? I'm just saying allocate an array, just don't put anything interesting in it yet. OK? All right, yeah, question. The question is, what is the purpose of a CC_num array? So the goal of the algorithm is that we need to find the partitions of the graph into connected components. Okay, so how do we express that? Well, one way to express that is that for every vertex, I tell you which connected component it sits in. Okay, so I can call them blue, red, and green. Then I call them 1, 2, 3, and 4, right? So they just need to have distinct names. Okay. Oh, it's a very simple algorithm. Okay. But at least it does something useful. Notice this is basically depth-first search. Okay. Together with the explore procedure. Okay, and it was basically doing bookkeeping as you travel. Okay, so it turns out that there are many useful things you can do with this type of bookkeeping information. So what we're actually going to do next is collect very fine-grained information about the graph as we travel through it, and then we'll talk about how we make use of information that we collect as we travel through the graph. Okay? So instead of keeping track of, say, connected components, we'll keep track of very specific things. Okay? And then, given this information after you do that first search, you can tell a lot about the structure of the graph. Okay? That's kind of the plan right now. So we're going to, yet again, modify something that looks like this, okay, and something that looks like that. Okay? Right now, it might not be clear why we're keeping track of that information, but then I'll make it clear immediately after. Okay. So I'm gonna put it right underneath here so that we can see the analogy. Okay. And now this is the actual DFS. So because when people think about depth-first search, it actually does something useful. So this is the actual depth-first search. So as before, for every V in V, we're gonna start out the visited flag to be false, because we haven't done anything yet. And then for every vertex, we're going to maintain 2 integers. Okay? Something that is called the pre-number and the post-number. So we're going to be pre-V and post-V. And we start them out as bottom. Okay, just some symbol that it means initialized. What are these numbers? Well, as we do depth-first search, we're going to start a clock. Okay? What does the clock do? It does tick, tock, like it continues like that as the algorithm goes. Okay? And what we want to do is we want to keep track of the time when we start exploring a vertex and the time when we stopped exploring it. And kind of even more precisely, there's an implicit stack here, right? Because what is this exploration doing? It says, put V on the stack, right? And you keep exploring other things, which are then put on the stack, and you pop them off the stack only when you're done exploring them. You notice that it is a stack because the poor V, that was the first thing that was explored, is at the bottom of all these other things that are being explored as he waits at the bottom. Okay? So this pre and post denote the time at which a vertex enters a stack and exits a stack. Okay? So now we're going to sort of realize this, this plan. So we're going to set the clock at the very beginning to be 0. Okay? And now for V, for every V in V, as before, if it is not visited, then we're going to explore it. And inside explore, we're going to set these numbers. So explore, this is the actual explore procedure. So when you start it, just like before, we're going to set visited of v is true, because now we are visiting it. And now we're going to say, OK, so if we are visiting it, that means that we're putting v on the stack. So we say pre of v equals the clock, whatever the clock value is right now. Now, we have done an operation, so we need to let the clock tick. So we say clock plus plus. OK, so it goes up by 1. And then, like before, we consider all the edges. So for every v, w in E, if we haven't visited w, we explore it. Right? And this is it. This could go on for a very long time, right? So exploring w, then explore w prime, w double prime. In the meantime, v is at the bottom of the stack, right? Whenever all these explorations are done, and we've done exploring all the edges, that's when we are removing v from the stack. So after this potentially very long wait, we're going to say, OK, post of v is the clock. So it's the time where there's nothing else to be done about v, and we increase the clock because we have done an action. So clock plus plus. OK? Again, what are the differences here is that we're maintaining this information, we're maintaining the clock. OK? We are sort of doing an action here, and we're doing an action here. So this is the interval of time, interval on stack of v. OK? So this is a lot of fine-grained information. And now we can start sort of thinking about what we can read off out of this information. OK? So first, are there sort of syntactical questions of what I've written? Yes? Right now, we're not, because we'll be able to elicit this information from this other stuff instead. Yeah? Well, because suppose for a moment that there's no edges to explore, right? So if I put v on the stack, and I remove v from the stack, I'm doing these actions at 2 different times. So just because of that. Yeah? Excuse me, this one? So here that was just to emphasize that it's not the same as that explore. Here, I'm just redefining DFS and explore to be these. Because the ones that we had written earlier, they were just tentative. They were not really doing anything too useful for us. I wanted to first discuss properties about them, for example, like this one, which continues to hold true. We're just doing more bookkeeping. I didn't want to get distracted by the bookkeeping while we discuss things like these. OK? So the previous DFS and explore were not really doing anything useful. Now we're starting to do some interesting bookkeeping. And you will see that actually this bookkeeping will let us, once we have this pre and post information about every vertex in the graph, we can actually read off some interesting things. OK? I still need to demonstrate that. But are there more questions about this algorithm? Yeah? Why am I what? Why am I tracking the time? Because if I don't increase the time, then everything happens at the same instant, and I don't know what's happened. Oh, well, now we have this information. We have, for every vertex, the interval of time that it has been on the stack. Now, a priori, this sounds like an extremely boring piece of information. But no, if we get to the next few things, then we'll see how to use it. Okay? So we plan to use, it's not like our goal was to find a time on the stack. We want to find a time on the stack as a means to an end. Okay? So let's first talk, for example, about connected components. Okay, we just sort of did something useful, and now we're doing something else instead. Can anybody tell me how I can read off the connected components from the stack information in the undirected case? Yes? Right, so yes, you're going in the right direction. So now we want to start thinking about how these intervals relate to the structure of the graph, okay? So here is, so what should I erase? Maybe let's erase here. So to every vertex v, we can associate to it an interval, pre-v to post-v, right? I mean, that is the information that we have obtained. And for example, when you have an edge that looks like uv, okay, then we know that the intervals for u and v satisfy a certain relation. So in particular, they will either look like this. So suppose for a moment that I visited u first. So I have an edge, uv, OK? So either I went first to u or I first went to v. There's no other option, right? Suppose for a moment I went first to u. Then I claim that the intervals will look like this. Right? Because I first went to u. OK? Did stuff. Among the stuff I did, I visited v. Right? I could not have popped u from the stack before I'm done with v, right? Because it's a stack, right? Things on the top have to be removed first. And it means that it looks like that, right? Or it could be that even though it's an edge, I somehow started exploring from w, and I made my way to v first. Okay, and this is an undirected edge. So maybe I visited you later. Okay, so maybe it looks like this. Sorry. Right, but they're not disjoint. Okay. So what I'm saying is that if u and v are in an edge, either way it will be that one of the intervals is contained in the other. More generally, I could have said the same if u and v have a path between them. Okay? So what this tells me is that when I kind of draw these pre and post numbers, they look like parentheses. Okay? They're kind of balanced. They're not crossing each other, right? So if you open a parenthesis, you can open another one, but you must close it first before you close the outer one, right? And then maybe you close all parentheses and you're back sort of to no parentheses, and you can start another block of parentheses. Okay? When you start another block of parentheses, that is a new connected component, right? Because that is the only moment where you could have closed all parentheses, is when you're done exploring the outermost guy, right? And when are you done exploring the outermost guy? When you've explored everything reachable from it, right? So if you kind of write down the parentheses, you can count the number of connected components by looking at the base outer parentheses. So here, there would be 4 connected components, OK? Because this is one connected component, this is another connected component, right? And things maybe look even more complicated. Okay, let me just maybe open another parenthesis inside here, and you close that one, right? So you could have 2 parentheses maybe like that, OK? So we didn't lose information about what it is that we were doing earlier, okay? And so we can still, with this information, elicit the connected components. And now we're actually going to use this information in an even more sophisticated way to try to understand directed graphs, okay? What are the questions about this? I hope this makes sense. So for the directed case, yeah, we have 15 minutes, and let's do that. I'm trying to figure out. OK, I'll remove the other one. OK. So the next goal is we want to understand directed graphs and connected components. And while I erase, so maybe you have a word that you would like me to pronounce for you. Is there one? Does anybody have an Italian word that you want to understand how to pronounce? No words. Otherwise, I will ask. Come on. You never eat. Oh, that is actually not a word, a phrase. Table for three. Un tavolo per tre, per favore. Un tavolo per tre, a table for three. So it's actually, I remember, so I was an undergraduate at MIT, and I used to row. Actually, that was a thing I did before research. And I remember before races, where would you go? Olive Garden, right? Because it's the ratio of carbohydrates to price is like very high. You have to stock up on carbohydrates before a race. And I remember my coach had ordered a bunch of these things. And this was maybe first or second month in the US in my life. And I never knew that you could pronounce this word as bruschetta, which is horrible. There is, and it is also, it's really attractive to pronounce it that way, because look at here, there is sure, of course, right? But as you've seen in past lectures, CH is consistently and systematically K, right? So really what's happening here is something else. This is bruschetta, right? And for a moment, I didn't know what my coach was even saying. What is bruschetta? I have no idea. This is bruschetta, actually. So for those of you who don't know, this is the grilled bread with tomatoes and basil on top. So that was the first of a series of discoveries about how Italian Americans managed to sort of not educate. So there are many Italian Americans, among other things. It's a population of immigrants. Anyways, so let's go to connectivity of directed graphs. So here, things get more complicated in the sense that the first thing that breaks is what? In a directed graph, what nice structure had we before that we don't have anymore? Yeah? Right, so in particular, what does that mean? What? The symmetric part, right? So reflexivity, you're definitely connected to yourself, but the symmetric part doesn't hold anymore. So in particular, I cannot just say that, oh, if you're connected to V, then you're also connected, V is also connected to you. Okay, so we have to strengthen the notion of the relation to talk about kind of strongly connected. Okay, and we don't really say strongly connected, we say connected anyways to mean a stronger definition. So we're going to say that U and V are connected if so you can go from U to V somehow, right? And you can go from V to U also somehow, maybe it's a different way to get back, right? Doesn't matter. But sort of they are connected if you can go in either direction according to some path, okay? Even before, you could have used different paths, but you could, in particular, use the same path, right? Because the same path can go at every edge is bidirectional. OK, so we have strengthened the definition of connectedness to make it symmetric. So we continue to have a partition of the graph into strongly connected components. These are called strongly connected. So, so we're going to try to understand that, OK? So this is going to be a goal. Understand strongly connected components. Okay, but it's going to take a little bit of time. Probably it's going to go into next lecture. And in order to build up to it, we want to first study a set of graphs and a set of directed graphs that play a very important role. Okay, these are graphs that don't have cycles. These are called directed acyclic graphs. Okay? Somehow we want to first build some intuition about these in order to solve that problem. Okay? So directed acyclic graphs, also called DAGs. Okay? Acyclic means no cycles. Meaning that if you can go from U to V, then it is not the case you can go from V to U. And first question we want to try to ask is, how do we know from the pre's and posts that a graph is acyclic? Does anybody have any guesses? So we run DFS. We collect all this bookkeeping information about stacks, OK? And we want to try to kind of look at this pre and post information and try to figure out, is the graph acyclic? Well, we made this analysis for connected graphs. Actually, kind of not just this analysis, but the definition of connectedness kind of breaks down in directed case. We can actually not rely anymore on that intuition. But it was a reasonable guess. But the answer is no. We cannot just look at that one. Yeah? Right, so this is a very good intuition, okay? So let's try to maybe look at an example, okay? So we want to kind of want to study the post orders, okay? Let's look at an example. Very small graph. Let's look at A goes to B. It also goes to C, and C also goes to B. Okay, it's a sort of three vertices, three edges, okay? Suppose that we start at A, okay? So I suppose that I run DFS, and in particular, I start explore directly on A, okay? Let's just write down what are the numbers that we get when we explore this graph, okay? So A will go on the stack at time 1, right? I don't know yet when it will go off the stack. For now, I just know it will go on the stack at time 1. Then we explore all of the neighbors of A. Say that we're exploring B first. Okay? So B goes on the stack at time 2. B is lonely. It actually has no neighbors. Okay, so we look for them, we don't find them, so we immediately remove it from the stack at time step 3. Okay, so kind of we're popping back. We go back to A, and we say A actually has another neighbor, C. So C goes on the stack at time step 4, right? Now we look at the neighbors of C. There is one, it's B. Okay, but B has already been visited, so we don't consider it. Okay? All right, so there's no other neighbors beyond B, which has already been visited. So it goes away from, get popped from the stack at time step 5. We go back to A. We have actually already examined all of its neighbors. And so A gets popped off the stack at time step 6. OK, now this is a directed acyclic graph, as I mentioned earlier. And in particular, in a directed acyclic graph, we can think about an order. Okay? We can order the vertices. Okay? And what I want to do now is I want to give intuition about how the order of the vertices relates to these pre and post numbers. Okay? Because in a directed acyclic graph, where do I want to go? I'm going to go in the running time here. Okay, maybe I was assuming a little bit of knowledge. I mean, how many of you have heard of topological sort? Ah, somehow I thought it was covered in an earlier course. OK, fine. So let's talk about topological sort. All right, so in a DAG, so let me first define that. In a DAG, a topological sort is an ordering of the vertices so that each edge goes from an earlier vertex to a later one. Okay? So let's, for example, look at this example. What is the topological sort of ABC? A, C, B. So let's draw it. A, C, B. So we have an edge going from A to C, one from C to B, and one from A to B. So in a directed acyclic graph, you can always find an order where kind of all the edges are moving in one direction, right? So why? Well, because pick any edge, right? So there is no cycle, so you can always pick one of the two to come first, right? That edge will point in the sort of in your right direction, right? A bad example would be to say A, B, C, right? In this case, yes, the edge from A to B goes in that direction. The edge from A to C goes in that direction, but this one is kind of not OK, right? So it's not a topological sort of directed acyclic graph. Now, what do you notice for this ordering and the information that we just collected here? Notice that, curiously, these two orders correspond, for now, to two different guesses, right? We have pre and post orders, right? There are two natural guesses. What if we just order the nodes by increasing pre-number, sorry, or by decreasing post number? Those are the only two reasonable guesses. And it turns out that those two, for this particular example, actually correspond to that, right? So suppose I ordered this one according to increasing pre-number. I would first put A, then B, then C. And if we did that, that would actually be a bad thing to do. Okay? So there's a counterexample that shows that if you take the pre-numbers and you make them increase, you're not guaranteed to get a topological sort. Doesn't mean maybe you will, but in this particular example you won't, so you're not guaranteed to get it. But if we look in decreasing order, the post numbers, for example, 6, 5, 3, because in this case, we do get a topological sort. Okay? And so now, what I want to argue is that you actually get this all the time, okay? So that DFS gives you all the information you need to compute a topological order of the graph. Are we together, at least for the example, okay? Do we agree that for this example, the post numbers in decreasing order, they really give us the correct answer. And increasing pre-numbers do not. Okay? All right, for this small example, things are easy to see. So let's move this up. There's a claim here. That if you consider vertices in decreasing posts, then you get a topological sort. Okay? So why is that? Actually, you know what? I want to give a proper explanation to this one, and we have like 2 minutes left. So I think we're going to pick up from here next time. And the goal will be to understand better the structure of pre-post numbers so we can apply it to understand the connectivity of directed graphs.